So our goal today is to cover this idea called related rates. Only two real words, related rate, first of all, what is that? And next, guidelines for solving related rates problems. Now in a nutshell, what this means is we're going to study practical applications of the chain rule with mystery functions. Now, practical applications is of course just code words for story problems. Yep, I can feel you groan from miles away. So what we're going to have is we're going to have some story problems here that show us where the chain rule happens and how implicit differentiation can actually help in a really practical setting. So our motivation for our practical application is that an oil rig has begun to leak oil into the Gulf of Mexico. And so far we've been able to collect the following facts. First, the oil is making a cylindrical pool on the surface of the water, and this pool is staying about 1 foot deep. The next thing we've been able to figure out is when the pool had a radius of 200 feet, it is measured to be increasing in radius at a rate of 5 feet per minute. And later, when the pool has a radius of 300 feet, the pool begins to increase in radius at only 4 feet per minute. So isn't this great? I mean, we've got this leaking oil, but it was increasing at 5 feet per minute in radius before, now it's only increasing at 4 feet per minute, so everything seems good. But a really important question here is not so much how fast is this pool increasing in size, but what is the rate of change of the volume coming from the pipe? And so this problem is called a related rates problem, because what we have is we have the rate of change of radius is going to be somehow related to the rate of change of the volume. And since these two things are somehow related, it's called a related rates problem, because we're going to figure out how to relate the rates. So what we want to do is we want to solve this related rates problem. We really want to figure out, well, what do we know about the volume? And to do this, I'm going to give some guidelines, but here I've also copied the information from our problem. So the first thing we want to do is we want to identify all given quantities and our quantities that are to be determined, and finally make a sketch and label the quantities. So these all happen sort of somewhat of an order. So the thing is we've got this pool of oil and it's forming a cylinder here. And what we're given in the problem, so please excuse my poorly drawn cylinder, that's a cylinder, trust me, is we've got that it's 1 foot deep, and we know it's got this radius here, and we also know that there's a volume going on. And so another thing I want to do is I want to give these names. So R of t is going to be a function that gives the radius as a function of time. Of t time. And also volume, V of t, will also give the volume of oil, again as a function of time. And we know some things about this. Now, what we can do is if we look at our problem here, we're given that when the pool has a radius of 200 feet, its radius is increasing at 5 feet per minute. So let's call this time 1. So we know that the radius at time 1 is equal to 200 feet, and we know the rate of change of the radius, dr dt, at time 1 is 5 feet per minute. So this tells us some very important things are happening at this certain time. The radius is 200 feet, and the change in the radius, dr dt, with respect to time is 5 feet per minute. We can also do is we can say when it has a 300 foot radius, it's increasing at 4 feet per minute, and this will be time t2. So now we know that the radius at time t sub 2 is going to be 300 feet, and we also know that the rate of change of the radius at this time is going to be 4 feet per minute. And so this brings up a really important point to think about. Almost every letter is a function of time, okay? So the radius is a function of time, the volume is a function of time, and all these things are going to be functions of time, so we can take their derivatives and talk about their rates of change because they are functions. And of course, what I want to find, so I'm going to move this over here, is I want to know what the rate of change of my volume is at time t1, and I want to find the rate of change of my volume at time 2. So these quantities, we want to read them as the change in the volume at certain times. So the second step in this process is to write an equation involving the variables whose rates of change either are given or are to be determined. And so the key is that we know stuff about dr dt, we want to know about dv dt, so what we want to do is we want to somehow connect the variables v and r together. And in this case, since we're given that we have a cylindrical pool, the equation we want is that the volume of my pool is going to be equal to pi times r squared times h, where v stands for volume, r stands for the radius, and h stands for the height of my cylinder. So let's draw a quick diagram over here. Once again, excuse my cylinders. Has height h, radius r, and volume v. And the thing to remember is that these are all functions, okay? So we really have v of t is equal to pi times the radius of t squared times the height of t as a function. So functions, functions, functions. So the third step is that using the chain rule, we want to implicitly differentiate the equation with respect to time t. So our equation was v is equal to pi r squared times h. So this means we need to take now the derivative of everything with respect to t. So we need to take the derivative of the left-hand side, and we need to take the derivative of the right-hand side as well. And so this is a good place for you to stop and think back to your implicit differentiation and to take a crack at it and see what you get. So pause the video and try it. Okay, so when we take the derivatives, the left-hand side isn't going to be too exciting. It'll just be dv dt, just like if it was y in there. The variables here, they don't match, so we just end up with our derivative. The right-hand side is a bit more interesting here because we really have two functions, so we need to use the product theorem to take the derivative. And so we'll stick the pi with the r squared as the first function. So what we really end up with is a derivative of pi r squared times h plus pi r squared times the derivative of h. And everything, of course, is with respect to t. So we can work through this derivative here, and we're going to get 2 pi r dr dt times h plus pi r squared times dh, in blue of course, over dt. So this is our derivative. This is our equation that we can work with from now on. The last step in the process is to substitute into this equation that we just found the derivatives of all known values for the variables and their rates of change, then solve for the required rate of change. Now in the previous step we had calculated this to be our derivative here, and so what we want is we want to figure out dv dt. The problem is we've got to figure out what to do with everything else here. And so we can go through and think, well, what do we know? Well, one of the things we know is we know what our radius is going to be. Our radius, we said, was 200 feet. So we know that r is going to be 200. We also know the pool has a 1 foot depth. It's 1 foot deep. So this means h has to equal 1. So we're doing pretty good on this first part here. Not too bad. And we also know that dr dt at time 1 is increasing at 5 feet per minute. So we've also got the radius. We've got all those first terms figured out. Next we need to figure out, well, r squared is no big deal. We already know what r is. So we're good to go there. But what about dh dt? Well, we know that our height function, the height of t, the depth, is always 1 foot. So this means that dh dt is the derivative of a constant is 0. That really helps us out. dH dt is 0. So now it's a matter of simply substituting everything in. So we can figure out now that the change in the volume at time t1 will be equal to 2 times pi times the radius, which was 200 feet, times the rate of change, which was 5 feet per minute, times the height, which is 1 foot. So when we multiply this all out, we get approximately 6,283.19 cubic feet per minute. So this is how much oil is being pumped out at that first time that we measured there, when the radius was increasing at a rate of 5 feet per minute, and it was increasing at a total radius already of 200 feet. So we're losing about 6,300 cubic feet a minute of oil. Now we can also use the same equation we just found in order to figure out what happens now when we have a 300 foot radius. In this case, R is just going to be 300. dr dt at time t2, we said that this is going to be 4 feet per minute now instead. And again, our height will always be 1 foot. So in this case, what we have is that the change in volume with respect to time at time t2 is going to be 2 times pi times 300 feet times 4 feet per minute times a height of 1 foot. And when we calculate this, we get approximately 7,539.82 cubic feet per minute. So this is bad. Even though our oil is getting sort of bigger, slower, the problem is that we're actually having an increased amount pour out. So what we can think about is at time t1, our radius was only 200 feet, but the problem is that when our radius got out here to 300 feet at time t2, it's increasing actually faster. We have a bigger volume coming out, even though it's sort of slowing down how fast it's increasing in size. So this is why related rates are important, because just because one rate is decreasing, that doesn't mean that overall all rates are decreasing. We actually have more volume even though the pile isn't getting bigger as fast. So that's the big idea, that we're getting more volume even though the radius is slowing down. So here we've got another example problem, and as always I encourage you to take a moment and to try to work through this problem on your own and then compare it to what we get. Okay, so let's work through the process again. So the first step in our process is always to write down our givens and maybe draw a diagram. So givens and a diagram. So this is also a good time to read through our problem. So the problem says the ice cream machine in the cafeteria is going to be stuck in the on position, and the ice cream is going to collect on the floor in the shape of a perfect cone. Ooh, and we were even given the formula for our cone here. That's awesome. So rather than turn off the machine, someone measures and finds the rate of change of the volume is half a cubic foot per minute, and h, the height, is equal to 3 times the radius. So let's go ahead and start by sketching a diagram. So we've got ourselves a machine. This is my machine, and my machine is going to pump out ice cream. And for some reason, ice cream is red. Apparently it's strawberry ice cream today. Ooh, so we got a nice looking upside down cone there. And let's see, what things do we know? Well, we know that we have a height. So let's give this thing a nice little height. Let's give this cone a nice little radius here. We've got some volume action going on. So V will be for volume. R gets to be the radius. H is the height. These are all givens. H is given as 3 times R, our radius. We also have another important idea here, is that the volume, the rate of change of the volume, is half a cubic foot per minute. So what this tells us is that dV dt is going to be 0.5 cubic feet per minute. And the last thing we might be interested in knowing is what we want. We want to figure out how fast the radius of the pile is increasing when the radius is 1 foot. So we want dr over dt, the change in radius with respect to time, when r is equal to 1. So the next step in our process, of course, is to find an equation. Now, fortunately, the problem was very nice in this case. The equation we're going to use is the fact that the volume is 1/3 pi r squared times h. The key to remember is that these are all functions. We have a v of t, we have a 1/3 pi, those aren't functions of course, r of t squared times h of t. So that when we take the derivatives, we're going to have to remember that these aren't simple constants floating around. These actually have to be computed as the derivatives of functions. Okay, we have to remember this. Almost every letter is secretly a function of t. It depends on time. Now the important thing is that sometimes you're going to have to build your own functions. You are going to have to come up either through geometry or formulas that you're supposed to know a way to build an equation to relate things together. It's not always going to be given for you. Alright, step 3 says we need to take the derivative. So let's write our equation here again just for kicks so we all have it going on. And now we need to take the derivative. So we're going to take the derivative. The left hand side is nice and easy, the derivative of v, and this is going to equal the derivative of 1/3 pi r squared times h. So the key here to recognize is here we have one function and there we have another function. 1/3 pi r squared is one function, h is another function. So when we take their derivatives, we end up with dv over dt is equal to the derivative via the product rule. So we're going to take the derivative of 1/3 pi r squared times leave the h alone, add this to leave 1/3 pi r squared alone, and take the derivative of the function h. So we're going to have 2 pi over 3 r times, watch for this now, dr over dt, this right of course is because of the chain rule, times h, plus 1/3 pi r squared times dh dt. Some people are sometimes tempted here to just write 1. Remember, this is just the derivative of h with respect to t. Now in step 4 we have to remember what the heck we were doing. Well, our problem says we want to figure out how fast the radius of the pile is increasing. So what we need to do is we need to solve for dr dt in our equation. So what we need to do is we need to substitute in the numbers for everything else, but figure out what that dr dt is. So things to think about are the fact that, well, way back in problem 1 we had a lot of things that were given. We know that dv over dt is half a cubic foot per minute. This came from our problem. We know that we're interested when the radius is 1 foot, so r equals 1. We know that h is equal to 3 times r from the equation, so this will be 3 times 1, so h will be 3. So far we're doing well. We've got a lot of these letters figured out, but how in the world are we going to figure out dh over dt? Well, as it turns out, we have an equation. The equation, h equals 3r, we can take the derivative of it, and we end up with dh over dt is equal to 3 times dr over dt, which means we can just replace it with 3 dr dt. So what we have now is, after doing all our replacements, we've got 0.5 is equal to 2 pi over 3 times 1 times dr over dt, because we want to solve for that, times our height, which is 3, and I'll put that in blue, plus 1/3 pi radius squared times 3 dr over dt. Okay, so now what we need to do is we need to algebraically solve for dr dt. This is the standard method you use to solve any equations. I'm going to skip a lot of the algebra here, but what we can do is we can solve for dr dt, and we're going to have dr over dt is equal to, it's going to equal approximately 0.0 0.5305 feet per minute. I was just waiting to make sure you remembered the units. So this is what this means, is that this pile of ice cream is not moving too fast on the ground. When the radius is 1 foot, it should be more than enough time for someone to hopefully unplug that machine and clean this up with a mop before it makes a mess. But anyways, this is how you go about solving these related rates problems. So for in class tomorrow, you have a couple to try, and then we're going to spend the next 2 days in class working through these problems in your groups, because they can be a little bit difficult, especially the part where you have to make up your own equations. As always, try the problems and come to class, take the quiz on the video, post a question on Blackboard, and I will see you in class, or maybe before in office hours.